In this video, we'll be talking about implementations of digital to analog converters. How do we actually implement them and get them in hardware? And we've got different methods available to us, software-based methods and hardware-based methods as well. In particular, we'll go through these four of them: the R2R ladder, the binary weighted DAC, a thermometer coder DAC, and the one that we'll be using mostly in the labs, which is PWM or pulse width modulation. So our first one is our R2R ladder. And basically here, it's a very simple DAC in that we have just a whole series of highly matched resistors. And we create them in this ladder formation, particularly if you turn it on its side. Basically, it's operating as a whole array or a whole series of stacked voltage dividers. And we know with a voltage divider, we can calculate the voltage at any point pretty simply if we know what our resistors are and what our full scale voltage is and our ground point is. Well, here we can do the same sort of thing. If we know what those bits are feeding into each of those different branches of our voltage divider, and we know what our resistors are, we can work out what our analog output will be. Basically, each of our pins here, our bit inputs here that come from a microcontroller or some digital logic or something like that, will form one bit of resolution for our DAC. So if we had 8 input pins here, we'd have an 8-bit DAC, or 8 bits of resolution that are available to us. I mentioned before we require well-matched resistors to make this work well, and we have some voltage spikes that can occur at some of those major intervals, those major crossings. And think for a moment, going from 0, 1, 1, 1, 1 to 1, 0, 0, 0, 0, depending on which one of those, the 1 and the 4 ones changing to a 0, or the 1 changing to the 0 changing to a 1 occurs first, we might get a voltage spike where it spikes up momentarily as it sees 1, 1, 1, 1, 1, or something that spikes down as it sees 0, 0, 0, 0, 0, just for a fraction of a second. So that's something that we need to be aware of, and we could use some filtering to filter that out.
What we have here is our R2R ladder DAC set up on a little breadboard. So we've got along here a couple of 1K resistors, and along here a bunch of 2K resistors, so double the 1K. And what we can do is we can very easily adjust by putting the resistor in either this slot or this slot, whether it's 0 volts or connected to ground like these ones all are, or in the next slot whether it's connected to 5 volts, which is our VREF value. So if we move our least significant bit from ground through to our VREF value, it gives us 0.616 volts output. Nice analog output voltage. And if we do our calculation, we've got a 3-bit R2R DAC here, so n is 3, to the power 3 is 8. We see our binary value is 1. 1 divided by 8 times 5 volts gives us approximately 0.6 volts. So we're pretty close. If we increase our next one and step up by 1 and decrease this down by 1, it gives us about double what we had before. We step up and put the value 3 in there, we increase by about another 0.6 volts as well. If we step these low and move our most significant bit, it should give us about half our full scale voltage, so about 2.5 volts or so. That's a very basic example. Now obviously these resistors aren't perfectly matched, but they give the picture of how we can create our own DAC using a few resistors and voltage dividers like this.
Our next one's our binary weighted DAC, and here, rather than using a ladder of resistors, here we're using a resistor for each bit of our DAC. And we arrange them in a series of binary decades, so rather than all being matched exactly the same, here each successive resistor doubles in the resistance that it has. We feed these all together into a summing amplifier, and these can be quite difficult to produce. The reason being, before we had to match a whole lot of resistors, which is reasonably easy to do. We could get them out of the pack and measure them all, or we can laser trim them to get them very well matched in terms of resistance between each other. Here we've got resistors that start at maybe 1K and then 2K and then 4K and then 8K and doubling each time. We also need a very wide range of resistors, because if we want something like a 12-bit DAC and we start at 1K, well, we're going up to 2 mega ohms. So with that doubling, it takes off very quickly and increases very quickly. So here's an example of what it looks like. We have all those resistors starting at 1K, 2K, 4K, 8K. They all go into that summing point there with an amplifier with feedback loop there. And we can see in our outputs that we've got there, as we change our input values to A, B, C, and D, which are our different inputs to our DAC, our output value is going to change as a result of it. And there we've got an example of 1001 going into there, and as we sum them up and our feedbacks pass through, we get an output, our analog output there, of minus 5.625 volts. Our next one's what we call a thermometer coded DAC. Now in our binary weighted one, what we had was a single resistor for each bit of our DAC. Well, thermometer code, we take it a step further and have a single resistor, or a current source for that matter, for each possible value of our DAC output, or each step that we're having in our possible analog digital outputs. So for example, an 8-bit DAC, where we've got 256 different levels, we'll have 256 different resistors. You can see this is really taking off very quickly. They can be very fast and high precision, but as you can imagine, with this many resistors, it starts getting difficult to actually implement in hardware, particularly if we want a high resolution DAC. Now, when we talk about an 8-bit DAC, we're not actually talking about a very high resolution DAC at all. It's a fairly low resolution DAC. So it's starting to get difficult at this particular stage. We won't go much more into thermometer coded DACs in this course. The one that we will be using a lot though, particularly in the labs, is pulse width modulation, PWM. And this allows us to create a software implementation very easily and create analog-like outputs from our digital domain from code that we're actually writing. Essentially what we do is we take a square wave and we modulate the duty cycle of this square wave. We keep the period constant, so it's always going to be the same, and you can see that in these pictures here. The period remains constant, but the on time to off time, or our duty cycle, changes. And as it changes, it will alter the average voltage output. So if you think you average it over that period, those first ones on the far left there, there'll be a fairly low analog output voltage in the top column. But towards the right here, in the top column, it's about 50-50. So the voltage is going to be about halfway between its maximum voltage. Down the bottom on the right here, it will be about its full scale voltage. So how do we actually implement this? And you'll be doing this in the labs. Essentially what we need to do is be able to adjust our on-time to off-time ratio. And we'll have, for example, our smaller pulses up the top there, our larger pulses down the bottom, our smaller pulses giving us a smaller analog output voltage, our larger pulses giving us a larger analog output voltage. So we need some way in our software to adjust our on-time to off-time. And doing so, we want to make sure that period remains constant. There's a few different ways we can do it. We'll talk about them in a bit. One other thing that we want to do is, when we're talking about analog-like voltages that we're kind of generating here, when we look at these sort of voltages here, they don't look very analog-like at all. They look like a whole series of digital pulses, high and low, high and low, high and low. Doesn't look very analog-like. So what we can do is we can put a filter on there. We put a low-pass filter on there. So it filters out the high-frequency noise, effectively filtering out most of the switching noise between those pulses, and it kind of averages them out a bit. It gives us something that looks a bit like an analog signal. Our capacitor value here needs to be fairly small, otherwise our response time of our DAC will be too low. And here's an example of something that we actually use in one of the labs where we've got a first order, so a very simple first order low pass filter. It's a RC filter, and our output looks something like this. Before our filter, you see we've got those highs and lows that we're expecting there. Afterwards, we've got kind of little peaks and troughs, but they're actually quite close together, a fairly small little ripple that we have there. Now we can significantly improve that ripple by having a better filter on there. We have not just a first order filter, but maybe several orders to take out some of that extra ripple that we've got there. And in doing so, we get a better representation of our analog voltage output.